Good evening, everyone. So I hope you all are okay. So today we start our new session. So meanwhile, I will check if any of you have any query, earlier query. Then otherwise we'll start. Okay. Hello. Okay, so I think we can start from where we left last time. Okay, so last time we were point. This is the thing we have done last time. So 1 second. Here, let me share the screen. Share my screen. So these are the things that we covered last time, I guess. There are some assignment problems that we have left for this time. So last time we talked about the several conservation equations for fluid motion and how the flux is changing, and conservation of mass, momentum density and flux that changes with time, and conservation of momentum. This time also, if you see, I'll give you some time. So we solve the Euler equations, and then for several compressible and incompressible flows, Laplace's equations, the steady flow, how it will change, and then so we have solved the sample assignment problems. Okay, that when we consider a fluid through a smooth pipe and all, so those things. Okay, these we have solved, right? So no need to record them. But then the assignment problems, I told you if you have any problem with that, you can convey the same. Okay, I think it fits well. Okay, so here, yeah, the assignment first questions. They consider fluid in horizontal tube. Let the fluid pressure at position x equal to 0 be P1 and that at position x equal to R be P2 with P2 greater than P1. Which of the following statements are true? Okay, you are given the options. But if the fluid is perfectly inviscid by zero viscosity, or the fluid will accelerate in the particular direction. If the fluid is perfectly inviscid, either that means that ID is zero viscosity, the fluid will accelerate in the negative x direction. If the fluid is quite viscous, honey, the fluid will flow at a constant velocity in the negative x direction. If the fluid is quite viscous, the fluid will flow at a constant velocity in positive x direction. You should be able to uh, figure out this. Right? Sorry, why it is. Okay, so how to answer that assignment? So now if you okay, so consider you can answer this question. I'll give you some time, or you can quickly give you the solutions of how it can be done. Okay, to consider fluid in horizontal tube. I think we have done similar type of question. Okay, so this is how it can be solved. That given this. Okay. The correct answer are B and C because the force on a fluid element is the gradient of the pressure, right? And the sign is opposite. I mean, basically it is that force and pressure gradient acting oppositely. Since the pressure at x equal to r is greater than at x equal to 0, because P2 is greater than P on, the force on the fluid element is in the negative x direction. Right, with pressure is more, so negative sign is comes before, so obviously it will be negative. If the fluid is perfectly inviscid, there is no opposing frictional force, so the fluid will accelerate in the negative direction. The more realistic case of finite viscosity, there is a viscous opposing force which balances the pressure gradient force, leading to dynamic equilibrium. In this case, the fluid will flow with constant velocity in the negative x direction. Okay. Question number 2 is, which are the true? Potential flows are irrotational. Viscous flows can be described using a scalar velocity potential. A smooth sphere moving through a perfectly inviscid fluid will feel no drag. This is easy. So you know that potential flows are irrotational. Why? Because why the fluid velocity can be expressed as a gradient of a scalar potential, right? U is equal to minus grad of 5. We have seen that earlier. So curl of U 0. Since the curl of the gradient is always 0, so potential flows are always rotational. Viscous flows are rotational. Okay, think of our familiar example of a paddle wheel placed in a only viscous flow that's shown in the lecture material videos. Therefore, they are not potential flows, and option B is incorrect. Okay, because viscous flow cannot be described using its velocity potential. Option C, a smooth sphere moving through a perfectly invisible fluid will feel no drag. Yes. Why? Because this is the D'Alembert's paradox, which is at variance with everyday experience. The velocity streamlines in this case are symmetric, and there is no scope for a pressure gradient from the front to the back of the sphere. Therefore, there cannot be any drag force. I will come back again to these questions if you have any query. A horizontal jet of water with diameter 8 centimeter and speed 25 meter per second impinges normally on a large stationary flat plate. The plate dimensions are considerably larger than the diameter of the water jet. The density of water is 1000 kg per meter cube, and you can assume the water to be perfectly cold. So pick the correct statements. Okay, this is the mathematical, so you can see the options. I will again come back so that you can calculate. I'll just give you a briefly overview. The Bernoulli constant is P plus half rho u square. Okay, because this is a horizontal flow, so there is no role of gravity as it is not moving up and down in earth frame. At the flare, the flow comes to a halt. Halt means where the flow is stopped now. So there is a U 0 and the pressure experienced there is the so-called stagnation pressure, equating the Bernoulli constant at some point far from the plate to that at the plate. You have P plus half rho square is equal to P plate. Since the water is assumed to be cold, we can take P is equal to 0. So we have rho, we have P, we have U. So we can calculate the Bernoulli constant. So we get the P plate. Okay. Where it is calculated. Okay. Yeah. So rho is there. Rho is 1000 kilogram per meter cube. U is 25 meter per second. All are in SI or MKS unit. So rho U square will be 25 times 25, right? How much it is? 625 times 1000 divided by half, right? So, so that will be basically 3,12,500 Newton per meter square. That is the P plate. This is the option D. Since the dimension of the plate is assumed to be much larger than the dimension of the water jet, the force exerted on the plate is just the area of the water jet times P plate. And area of the water jet is pi r square. And the r is here, how much? Diameter is 8 centimeters, so r is 4 centimeter. We convert that to SI, which is 0.04 meter times P plate. That is roughly is 1570 Newton. Okay. I'll come back again, or you can manually you can do the math. So question number 4 is city water tower is 50 meters high. What is the maximum speed of water that is spread from a hose that is situated at 1 meter above the ground? The water density is given, you know already. It is 1 gram per centimeter cube, or in SI 1000 kg per meter cube. So this question you can do in any units, CGS or MKS, whether whatever is convenient to you. It's good to be stick in on convention. Atmospheric pressure is given. Okay, you can take G. So what will be the right answer? You can calculate using the to get the maximum speed of water. The boundary constant you can use again. The half of rho u square. Okay, that is G times T minus 1. Okay, so how much is that? 49. Okay, sorry, pro is square. Yeah, so you'll get 31. Do this on by, so I will again. So pick the card statement. So the circulation of the velocity vector is conserved only for a perfectly inviscid fluid. So this is right, a ball, because the reason is the circulation of the velocity. Right. What is considered only for a perfectly inviscid fluid? True, because by the virtue of vorticity equation, so we already have gone through the vorticity equation, that the circulation velocity vector will be conserved for an inviscid fluid. Yeah. A ball spinning in a perfectly inviscid fluid will experience a lead by virtue of the Magnus effect. Not true, because Magnus effect by superposing a circulation on the potential flow solutions. The magnetic effect is observed only when the spinning ball drags along the boundary layer surrounding it, causing it to spin as well. If you want to use the simple potential flow solution, instead of using the more complicated solution with incorporated viscosity, we need to impose a circulation. The statement C is also false, because when the smooth sphere immersed in a perfectly inviscid fluid flowing past it at constant velocity, the tangential velocity at the surface of the sphere is zero, because it's only in the presence of the viscosity that there is sticking on the sphere. In the absence of viscosity, there is infinite tangential slip. Statement D is true by definition, because for a perfectly invisible fluid, only the diagonal terms of the pressure tension are non-zero. Obviously, because for perfect invisible fluid, the diagonal terms can't be zero. All the diagonal terms can't be zero. No, no diagonal terms be zero, because otherwise the determinant will be zero, right? Yeah. The diagonal terms represent shear stress, which are relevant only in the presence of viscosity. So go through these questions again. I'll be waiting here for you. So yeah, go through these questions again, and yes. Okay. So let me wait here for you where my screen goes. Yeah, so I'll be waiting here for some time. So you go through the questions again and again, then I'll be able to answer to your. Okay. Okay, so I hope you get. Circulation of the velocity vector is basically the vorticity. It will be conserved, right? Where you can face problem is that the ball will, the spinning ball will feel drag, not like lift, right? And it makes it spin. Or we need to make a circulation for the spinning ball. So yeah, so the 4 you should do it the math. There can be some typo. Uh, there will be row is cancelled out. So this is row GH, right? You know the row GH, 50 meters high, but this is 1 meter from the ground, and half row is square, so row cancelled out. You will be just simply 98G. What is this 98G? Is 980, right? And then if you root this, root of that, hello, will be nearly 51.30, right? So basically option C. Right. Okay, spend some more time on this question number 3. I'll be here. So I hope you're able to understand question number 3. The Bernoulli constant is the stagnation pressure. Right. Question number 2 is also I've discussed. So I think we'll discuss this covered. We'll discuss some next part of it, I guess. Yeah. So let's come to week 3 where we talked about some circulation. The question of circulation that we have dealt now just in the assignment. So circulation is defined as the integral of u dot dl, the path integration over a closed curve C. Or if you use the Stokes law, so it will be like uh, curl of u dot dA, that is omega dot dA over a area A, right? So this is circulation is defined. The Kelvin's vorticity theorem is for inviscid, where viscosity is not playing any role, incompressible, where the fluid is not compressed, barotropic, where the pressure is following some form of the pressure is a function of density, fluids under conservative forces. Then dk dt, you to the perform the integration, it will be du dt dot dl plus u dot d dt of dl, right? So du dt over the time, we know already that this is du dt is minus grad p by rho plus grad phi, right? From the momentum equation. So an integration of, so grad phi dot dl is equal to phi d phi, right? So we can perform why this is that. I think you should know that grad phi dot dl is the integration of only, this is the only d phi, but this is the directional derivative, that grad phi along the length dl, just the d phi as the direction, and integration of d phi is phi, so it will be 0, right? With the conservation force. And integration of grad p by rho is again integration of grad p dot dl is dp, so dp by rho, so as p is a function of rho, and this is for a closed on, it will again be rho is constant, you can say, so dp pressure closed pressure is 0, so this whole term, and then this term u dot dt of dl, this is basically uh, so okay, don't confuse this. So dl is, you can think of that delta l, okay? So dl dt is velocity, so that is u, so but delta is there, so delta u, so basically this is u dot du, that is d of half u square, and that is again 0 because this is a closed contour. Okay, so we get dk dt is equal to 0, so k is constant, so k is conserved here. So we have assumed inviscid incompressibility rho is constant and barotropicity. But if you But double check. Have you really assumed this? What is that? This should be implicit, incompressible, and barotropic. So Magnus effect. So why cricket balls deep when spin? You know, if some people play cricket, so when the spin is made, right? When the spin is made and throw to the batsman, so it actually the balls actually dipped, right? So yeah, this is a circulation. U dot dl is not zero, so it basically dips. So when it is spin, it basically when it throw the ground, so it dipped to the ground. This is basically the Magnus effect. Spin ball inside fluid. Spin ball. Okay, this is drawing. So denser streamlines. If streamline is denser, the flow will be faster. See, at the streamlines it condensed here. So basically that makes the flow faster, circulation faster in the region, but not at that region. So that makes the dipping. So dipping of the ball here. The U below is greater than U above. So P below is less than P above. Right. U is more, so pressure will be less there. Then Bernoulli's theorem, steady plus inviscid. So this is the rotational axis. The force is acting this way, and velocity, as you see, these vectors are going along this way. So U is also along this way, right? So then, would you observe the Magnus effect without the added closed streamline around the ball? Question for you. Think about this. That if the stimulation are not closed like this, these are not closed, right? So do you still observe the Magnus effect? So for viscous flows, force due to pressure gradient, you know that this is the imputational box is considered along y. If this is y plus dy, this is the e direction, and this is the z direction. So this is dy dz, up as usual. Force due to pressure gradient is basically dp, dy dz here, dp along this surface. Pressure is this, and this is the perpendicular surface, so the force will be dp times area, and area is dy dz. So okay, dp dx, this is grad p, dy dz dx, so you get delta v, right? The scalar pressure viscous stress is defined as mu du dy, net frictional stress on fluid parcel u du dy, dy minus these things. These you have already covered in the lecture notes, I guess, but still I'm just revisiting those for you. Okay, viscous flows, force due to pressure gradient is this. So net frictional force on fluid partially mu d2u dy2 dy and dx dz along this surface. Then this is the dy and this is dx dz, so this surface. So this will be dy, all terms will be here. And then force balancing that mu d2 dy2 is equal to dp dx. So mu del square u is basically grad p. So this is identified as a viscous force because it comes due to the viscosity. See, there is the viscosity stress, right, in terms of zeta. So this is the viscous force. So we'll deal and come often with this term that mu del square u. We'll also see these terms in the equations, hydrodynamical equation. Mu del square u is grad p. The force, right? Grad p is basically force. Forget the conventional sign. Basically, this is force. So, so Euler equations, if we add the viscous term with it, with Euler's equation, this one rho del u del t plus rho u dot grad u c minus grad p plus mu del square u rho g. Euler terms, we will get the Navier-Stokes equation. Okay, Navier-Stokes equation. Viscosity, this is the pressure tensor. The P delta Ij, this is the diagonal term. This is the sigma is a 3 by 3 matrix. That will be basically a stressless matrix with all the diagonal terms are here. This is for the shear stress. So this, this is just because there is three terms on one third of PII. Right. This is how. So you get the Navier-Stokes equation. For more details, I suggest you refer to the lecture videos by Professor Subramaniam. And this is the viscous stress. Okay, remember. So then sigma will be we have del u del xj plus del u del I. Basically the op of cross terms plus b delta I delta t. Most general secondary tensor with first derivatives of velocity. Okay. So see mu d u dy like this. So b is equal to minus third a for sigma is stressless. Sigma ii just compartmentalize this term. Put I is equal to j. So put I in place of j. It will be same thing. So 2a del u del xi plus. So it will be 1. It will be 3 actually because there will be 3 terms. So 3b del dot u. So if this is 0, trace means sigma I. This is the summation convention. So if this equals to 0, then you will get what? Uh, okay, you will get this is the gradius, this is gradius. So this can't be 0 every time. So 2a is equal to minus 3b. So b is equal to minus 2/3 of a, right? So for like this, you can get the value of b. Okay, and your sigma is testless. So b value. So b is dependent of a. That's what it means. It's not independent. Why not sigma is a1 del a1 del x2 plus dot dot plus a1 prime this one. To simplify, assume isotropic viscosity. So if you consider isotropic viscosity, you will get this f surface as del p is del xj. What is from the lecture terms? F surface will be this inviscid flow. Okay, and zero. Okay, so these are some energy dissipation. Maybe I'll come back again to this viscosity next time. Okay, I'll come back again to lecture. Just for a brief overview, I can tell you that okay. No, I don't think I should do a brief overview. Should I do this on pen and paper? Will it be helpful for you or This is okay. See, this is just the F surface is defined minus grad P, right? And if I do the diagonal of diagonal terms, it will be minus del B del xi. The mu terms will be there of diagonal terms, B minus 2/3 of A, right? So mu is already there, so minus 2/3. And if you simplify this term, you will get Pij. Okay. Del square plus 1/3 grad of del dot U. Okay. So del square U is second order differential equation. At two boundary conditions in which flow U1 is equal to 0, UR is not equal to 0, and for viscous flows UN UR is equal to 0. So these terms cancel out. So for this fluid slips and for this fluid sticks because the velocity is 0. There will be just 0, and this fluid velocity is not 0, so it slips away. And energy distribution due to viscosity, basically the energy term del delta of half rho u square. See this term, this is the for incompressible flow, this is the term. At infinity flow velocity is 0, thus integrating a microscopic volume gives a distribution due to viscosity. Again, this term modification to Bernoulli's law due to viscosity. Navier-Stokes equation, the appropriate boundary condition. If you consider this flow, to close solution to Navier-Stokes thin pipe. I will come to this example next time. So I think sodium flavor. Okay. So for this, let's meet next time. Maybe we'll understand topic more. So see you next time. Thank you. Bye. Good night. I'm stopping the recording.